So today, we obviously live at the height of the information age. And computers have had innumerable and unpredicted effects on people's lives. Now, the key to this digital revolution is that any information can be simply represented as a collection of bits. With the advent of Moore's law, there's been an exponential expansion in our ability to store and manipulate those bits. This progression, where computing power doubles every 18 months, has been driven by the successive miniaturization of transistors and integrated circuits. But this can't go on forever, right? Because now we're reaching the point where many parts of a transistor are just a few atoms across. And this is a problem because, like it or not, we're entering the quantum world. Quantum mechanics is one of the biggest scientific surprises of the 20th century. Its new rules were so unexpected, we still sometimes call them weird or counterintuitive. Quantum computing is a new paradigm that seeks to exploit just these rules to process information in a completely different way. The basic idea is to replace the bits of a typical computer, which are either 0 or 1, with some quantum object, a qubit, that we can program information into its quantum states. Now, unlike a regular bit, a quantum bit can be placed in a superposition. Like Schrodinger's famous cat that's both alive and dead at the same time, a quantum bit can store both a 0 and a 1 at the same time. Now, this idea gives quantum computers, we think, a kind of parallelism that allows them to store massive amounts of information and accomplish otherwise impossible computing tasks. For instance, a computer containing just 200 qubits would store more than 10 to the 60 bits of classical information. So how are we going to build a quantum computer? Again, anything like an atom can serve as our quantum bits, but it's hard to see how to wire up individual atoms into something with the complexity of today's computers. At Yale, my colleagues and I are developing electrical devices that can serve as simple quantum bits. So using circuits composed entirely of superconductors and working at temperatures near absolute zero, we and others have succeeded in designing electrical devices whose quantum states can be programmed from the outside. And this technology has advanced rapidly to the point where we can actually perform a simple quantum calculation. So here's a little trick we did with this 2-qubit device that actually shows a quantum speedup. If I have a database with 4 locations and I'm looking for the special one with the only red card, classically I have to search randomly and it will take several tries. But our quantum device could find the answer in a single go. So far, the main limitation on this technology has been the fragility of quantum information. Our quantum bits tend to forget. But there's been exponential progress in the performance of these devices. In the 15 years since they've existed, we've seen over a million-fold improvement in the lifetime they can store information. And now it's reached the point where we think we can actually scale up. So where are we now, and what might a quantum computer actually be used for? If we look back at the history of conventional computing, it evolved through several phases, and the uses of computers evolved as well. Early on, all the applications were scientific or military, and it wasn't until Moore's law and the explosion of computing power that most of the current uses were even imagined. So our hope is that with quantum computing, there'll be a similar kind of an evolution. So today, perhaps we're at the analogous point that computing was in the 1950s. We have examples of a few working quantum transistors. Next, we need to devise the quantum version of the integrated circuit and master quantum complexity on a vast scale. So to avoid the accumulation of even tiny errors, we think it's going to be very hard to build a real computer. We need to build lots and lots of redundancy. Getting this trick, which is called quantum error correction, to work is the biggest outstanding scientific challenge today. So the discipline of quantum computer science, because we don't yet have the hardware, is still in its infancy. But what we already know about the applications are very tantalizing. So a quantum computer is exponentially good at solving quantum problems, like simulating the properties of a new molecule or a new material. A quantum computer might also help us devise a catalyst to sequester CO2 from the environment, or even perhaps to teach computers to be better at pattern recognition. Now, of course, as with the early stages of conventional computing, one of the biggest drivers so far has been its potential for breaking other people's codes. Now, paradoxically, it may be that quantum information and quantum mechanics can actually help ensure everyone's privacy. So quantum information has a special property in that it can never be copied. And this allows, we think, new kinds of secure communications that can't be eavesdropped. And finally, as with any radically new technology, we should expect that the best applications of quantum computers won't be known until we can actually build one.